Dear colleagues, dear Vice President Wood, dear Qiuting Huang, as head of the Department of Information Technology and Electrical Engineering, it is my great pleasure to introduce our colleague, Professor Qiuting Huang, who is sadly giving his farewell lecture today, after having been at ETH for more than 28 years. I am very sorry that due to the ongoing pandemic, the event can only proceed under, well, as you know, certain constraints and without the usual large gatherings and apero. But I'm delighted that it's possible that it can happen at all in person and that we can say goodbye to our dear colleague in person. Professor Huang was born and raised in China, where he experienced what one might say was quite a turbulent youth during the Chinese Cultural Revolution, when all primary and secondary education was suspended. Qiuting subsequently obtained his bachelor's degree from the Harbin Institute of Technology at China in 1982, and subsequently his PhD degree from the Katholieke Universiteit Leuven in Belgium in 1987. Following 5 years as a lecturer at the University of East Anglia in the UK, ETH was able to recruit him in 1993. He subsequently became associate professor in 1998 and full professor in 2001. In 2010, he became head of the Integrated Systems Laboratory and has been serving in this role since. He also served as the Director of Studies for our department between 2013 and 2015. In addition to his activities at ETH, in 2007, Professor Huang was appointed to a distinguished part-time Qiuting Huang Seminar Professorship by the Chinese Ministry of Education and the Qiuting Huang Foundation. In that capacity, he was affiliated with the Southeast University at Nanjing in China between 2007 and 2010. During the past 30 years, Professor Huang has pioneered research in a wide range of disciplines in integrated circuits and systems, with important implications for a vast range of areas from medicine to satellite technology. However, he is probably best known as a pioneer and one of the leading authorities in radio frequency, abbreviated as RF, integrated circuits for cellular communications based on deep submicron and nanometer CMOS technologies, now popularly known as RF CMOS. And for those in the audience without a double E background, CMOS, that's complementary metal oxide semiconductors. His research group published the world's first RF CMOS cellular transceivers at the prestigious International Solid-State Circuits Conference, abbreviated as ISSCC, often dubbed also as the Chip Olympics. And this was for the second generation GSM in 1999, and for the third generation standard UMTS in 2002. The research activities started at the time by 5 pioneering universities on RF CMOS for cellular, that is at ETH and KU Leuven, and wireless local network area networks at UC Berkeley, Stanford, and UCLA, eventually led to wide industrial acceptance and adoption of the technology, and the birth of an intensely researched discipline of RF CMOS wireless integrated circuits. Professor Huang subsequently founded a company, ACP Advanced Circuit Pursuit AG, to produce RF CMOS transceivers, the latest of which support 2G, 3G, 4G, as well as 5G in our cellular communication standards. Wireless communications started a revolution 30 years ago, culminating in the now ubiquitous smartphones that have fundamentally changed our world. And it is fair to say that Professor Huang's career has been intertwined with this wireless revolution. In recent years, Professor Huang's research activities have focused on highly sophisticated integrated systems for the Internet of Things, IoT, and wearable or implantable biomedical applications. For 5G cellular IoT, his research team integrated an entire cellular communications modem on a single chip. This is known as an RF SoC, system on a chip. On implantable biomedical devices, he won a special grant from GSK in an international competition called the Bioelectronics Innovation Challenge. And with this grant, he started building a multifunctional sensor node SoC for an implanted neuronal monitoring and stimulation system in order to study hypertension. Many large grants followed, which led to the development of highly sophisticated SoCs supporting ECG, EEG, and EMG monitoring, bioimpedance measurements, electrical and optical stimulation, photophlethysmography for pulse oximetry, perfusion and heart rate monitoring, and optogenetics. So these are, from a medical perspective, highly important innovations and have featured in publications in journals such as Nature Biotechnology in recent years. During the 50th anniversary of the ISCC conference, Professor Huang was recognized in the author honor roll, ranking 3rd in Europe and 15th in the world as one of the most prolific authors during the entire 50-year history of the organization, and his versatility also makes him the only author who has published in half of the 10 different disciplines of the conference, covering everything between microelectronic integrated circuits, covering all of the technologies related to microelectronic integrated circuits. And in 2013, at the occasion of the 60th anniversary of the ISSCC, he was again recognized as one of the most prolific authors in both the list of the past 10 years and the one for the entire 60-year span of the organization. Now, there are many, many more recognitions, honors, and awards that would deserve mentioning, but I don't want to take too much of your time, Qiuting. I just want to say it is incredibly impressive what you have achieved in nearly 3 decades that you have been at ETH. Thank you for everything you've done for ETH and to our department, in particular for the service you've given to our department as Director of Studies. With your retirement, we will be losing a renowned scholar and esteemed colleague. Fortunately, we still have you with us for a few days at least, and we intend to enjoy those days fully, as we will do now, I'm sure, in a great lecture to which we are very much looking forward to. Dear Qiuting, the stage is yours.
Thank you, class. And greetings, Vice President Wood, Vanessa, and all the colleagues, welcome, and students, family, and all those who supported me. Yes, so my life is intertwined with chips. And chips, in recent years, in the last couple of years, have very much been in the press. So let me begin with a quotation from a very influential news organization in the US. I try to explain how important semiconductor is, or otherwise known as chips. Indeed, the term is somewhat confusing. We refer to the same thing as chip, microchip, die, semiconductor, silicon, integrated circuit, and IC. They're mostly the same thing, used interchangeably according to different context. So the journalists try to explain what chips are, but allow me to pick out one important sentence to see what other people see our discipline. It says the impact that semiconductors are having on the world development exceeds that of the Industrial Revolution. The stakes are high. There's no talk about chips or semiconductor without mentioning Moore's Law, and those of you who attended the EE department probably have it up here because everybody talks about it. It fundamentally says we get smaller transistors every couple of years, and we can pack twice many transistors per chip every couple of years. So it is an amazing exponential run that has kept going for more than 60 years. And those exponential curves are difficult to read because the big numbers are so big. By the time you look at the smaller numbers, they are hooked on the horizontal axis. So typically, what we do is to plot it. Excuse me, just get my pointer on what we call the semi-log scale. So we take the logarithm of the curve to make it more readable and to show smaller numbers on that scale. So you can see today the transistor minimum dimension has come down to a few nanometers. The production level is 5 nanometers going on to 3, and we're thinking that 2 nanometers is possible, and even sub-nanometer is possible. And the latest Apple microchip, not so micro, contains 57 billion transistors. So what is an exponential? I think people have learned that during the recent event. So we write it that way. By definition, we say y equals e to the x, or a more general case, y equals that. And if you have 60 years of exponential run, every 2 years you double your number of transistors. This is about 2 to the 30th power, or 1 billion times more than what you started with. But it's not a definition. You can define it mathematically by an infinite sum, or by a differential equation that essentially says the derivative of that function is proportional to the function itself. The rate of change of a variable is proportional to the variable itself. The bigger you have, the faster you grow. It's kind of a positive feedback. And positive feedback is positive, right? Not for everybody. So if you look at, in the last couple of decades, the number of big companies capable of doing the latest generation of microchip technology have really come down almost in the same rate as the transistor size scaling. So we come down to 24 of companies to a couple of companies capable of doing that. So there are winners and losers because positive feedback, by the word itself, is never by itself. It's always cross-coupled or intercoupled. And those of you who graduated from EE department will recognize at least that circuit, even the software people, is called a latch, a digital latch. And it's 2 cross-coupled inverters, and those are the transistor representation of that. So typically when you have a latch and you reset it, so they start both sides start from ground, they will drift up, and both the red and blue will go up, right? And if the circuit is perfectly symmetrical, they should stay, nobody should get up first. So it's sort of an uneasy equilibrium that is hard to maintain. In fact, one side always goes up. It only takes a small difference. So one side always goes up and the other down. The winner takes it all. Even as both start off at a similar level, a small advantage, in this case, maybe just a little bit more current, a bit more stimulus, is able to tip it to one side. So your coin will go to one side, and once it starts falling, it's irreversible. So a stimulus can do that, and indeed blue, in this case, the blue side goes up and red one empty-handed. Or if one side is somewhat slower, has a bit more loading, more delay. And delay is not good, because once you miss that, this advantage could be overturned, and indeed, it goes the other way. Red can take it all if it's faster, and blue goes empty-handed if it has delay. And if you do a project, and if the project is exponential, not good to have a delay either. And this happens, exponential stuff happens to real life. The reason we wear a mask is the bad side of it. High volume products, markets, and so on often fuel exponential growth and rise and fall of fortunes. Semiconductor industry, Moore's law, are predicated upon high volume. And high volume things happen, and mobile phones and wireless communications are a salient example in that. See, if you look at what happens, a lot of the companies, those are well-known, recognized names, and some may not be anymore for younger people. They come up more or less the same, and they go up to incredible numbers. We're talking about several tens of million units per year and several hundred millions of units per year. Nokia at the time were producing, basically selling 1.5 million phones per day. Yet, some exponentials don't last very long. Recognize that shape? Not everybody makes it. So modern integrated circuit industry has largely been shaped by wireless devices because of the huge volume it has. So if you are developing or designing integrated circuit, you want to stay on that winning exponential. You don't want to fizzle out. So how do you do that? So there are different strategies. You build better transistors, more advanced technology node. But what if your rival has access to the same technology? So you don't have advantage there. Or what if your rival has more money for even better technology? Or you could do a better, faster design. But what is integrated circuit design anyway? Does it make a difference? And I was asked that very question during my interview for my ETH job, no less, by none other than Professor Niklas Wirth, among other things, the creator of the Pascal language. I'm fairly sure he was just being provocative to see whether the young professor can react, and I suppose I did it well because I'm here. But it does reflect a common thinking. Better transistors determine the outcome, and more advanced devices and technologies will be better. Indeed, many universities, many research laboratories, many companies hire device and technologists to help their cause. So where do we stand? So let me, humor me and let me go back to transistors and discuss a bit what is design. So with repeated scaling, transistors in an integrated circuit have become very abundant, therefore cheaper. And each generation have higher value we call transconductance. So for the same voltage, you get more current out, and therefore faster. That's a positive thing. They're lower in a thing called output impedance that essentially gives you less gain. That has some bearing for us. But the key thing is, although this planar technology of printing millions of transistors on the same chip is good, it's good in everything except in precision. It's not very precise. And for a digital circuit, it doesn't matter. But if you need passive components, mundane things such as resistor, capacitor, and inductors, you're out of luck. They're non-existent. Or if you do with whatever you can get hold of, they're not cheap, they're expensive. The positive thing is, if you do place those structures together close enough, they match very well. If your spaghetti is overcooked, they all get overcooked. If they are al dente, they all are harder to chew. And for analog circuit, people expect very precise outcome from your circuit. So the corollary of that is you cannot rely on absolute parameters. If you want to achieve precision, you have to do that with ratios of integrated circuit components. So here's an example of what most WE students have to endure, a single transistor amplifier. I won't go through that. The gain of that amplifier is a product of that transconductance and the load resistance. The problem is the product of GM and R sub L is not precise. And in fact, it could be off by a fairly large amount, 20 or 30%. A different example is what we call an op-amp-based inverting amplifier. The op-amp amplification is defined by the ratio of resistors. We do have lots of transistors inside that triangle sign called the op-amp. And the name of the game in a design is to make transistors invisible, hide them in the operation amplifier so that you only see the resistors and the ratio of them. And this entire thing relies on what we call the negative feedback with a very large loop gain. Oh, hold on a minute. Did I just drift into giving a first-year electronics course? Old habit, die hard, and this is my last time. I'll make it a bit lighter. Right. The operation amplifier is a ubiquitous and yet invisible device. It's found in all sorts of electronic systems, circuits, but they do not show up in the final transfer function, not if you design your operational amplifier well. When you see the op-amp parameters, you're in trouble because that means they're not perfect. So the performance of the operation amplifier is very often a decider of performance. And therefore, most transistors are tailored in that operation amplifier. So designing of an analog circuit very often boils down to design an extremely good operation amplifier. So there's key metrics. I'll just show a few, not all of them. We need very high gain, just as high as possible. Not necessarily precise, and yet if you can have high gain, you get precision. I won't explain why, students know. The other thing is it needs to have extremely high bandwidth. Bandwidth is synonymous to speed. If you have good bandwidth, you have good speed. It needs good phase margin, otherwise it may oscillate. Very fast stuff may oscillate, and you mustn't consume too much power, otherwise you run out of battery very soon. So here's an example, even if you design one transistor in there, and this is how the transistor looks in a layout view. It has a length. It's a PMOS transistor. A MOS transistor. It has a width, W. You put some current through it. I only show those three. And if you want to have high precision, high gain, you need long transistor or wide transistor, not so much current. If you want high speed, you want short transistor, lots of current, and very wide width. If you want phase margin, you need less delay, less capacitance, therefore small length, small width, and lots of current. And lots of current is not good. You want short current for the same transistor. So it's always like juggling different parameters. And indeed, I always tell my students, high precision and high speed don't come together. It's true in circuit design, it's true in life. So the design of a high-performance device is like training a rider for the MotoGP. It's a trade-off of competing demands and arriving at the best combination of qualities. So we go back to the performance metric. It needs to be very precise, and this guy is overtaking the other driver from the inside. Needs to be fast, name of the game, win the race. And if you push it too hard and have not enough margin, you crash out and the game is over. So for a design, trial and error will not lead to a good design because it won't pull competing requirements together. And here's how to not to design a circuit. So it's a famous fable by a Russian fabulist. And here's a recent modern example of a circuit, an A to D converter, where operation amplifier is important. So that's that op-amp again. And we talk about what we call a Bode plot, where we look at the gain and the bandwidth. So this particular one has 50 dB, 60 dB gain, and nearly 10 gigahertz of gain bandwidth. So a lot of my students who have taken the first year class would have been made to measure a commercial off-the-shelf amplifier called the op-amp 741, and that one has a gain bandwidth product of 1 megahertz here, so it's 4 orders of magnitude higher. So we always need a better amplifier. We always need a high performance, push that high performance there. And indeed, designing chips today is so expensive. If you don't design for high performance, you mustn't design it at all because it cannot be justified. So this one was designed for a 10-bit, 100 megahertz ADC for what we call 5G new radio. But I'm getting ahead of myself. Let's hold that thought for a moment and go back to the time where I finished the interview with Professor Wirth. The fixed-line telephone around the world were digitized in the late 70s, 1970s, that is, and throughout most of the 1980s. Or should I say, digitalized. Ironically, when we were doing the digitalization of the telephone, most of the circuits that were designed and fabricated were analog circuits. And indeed, at that time, the device that was most sold, highest volume device, is called the voice codec. That was sold a lot. So it was very exciting, and I called the tail end of it, did my doctor's degree in those things. And then came the early 1990s. Things were a bit quiet. They would talk about neural networks that are based on analog, but it was ahead of its time, and it was fizzling out. So I was thinking, and I was not the only one, was that the last hurrah for analog integrated circuit and their design? And indeed, a lot of the leading experts in the world were asking themselves the same question. So here at ETH, we kind of joined forces with a couple of leading organizations and organized this private workshop by invitation only in Interlaken. So where we just wanted to discuss among ourselves, there's no publication, no nothing, are the future trends in the integrated circuit. And among the invitees were some Nokia executives. People only knew Nokia at that time as a timber company. But they gave this talk, 10 minutes, on challenges for mobile phone terminal manufacture. So we were wondering the question, fixed line telephone was digitized, where do we go next? So we spent 2 or 3 days just amongst ourselves. The first day, we're about 40 people. Everybody gets given 10 minutes to say whatever they want to say, how they felt about future of integrated circuits. Second day, we formed small groups, brainstorming where things were going. Then central themes began to emerge and crystallize. And the third day, we sat down and wrote ourselves a white paper. And I was fortunate to work with Professor Hugo, visionary of the time. And we wrote ourselves a little report. So that report was not published, it was just actually everybody has a copy. And Marcus Helfenstein, who sat there, was the organizer there, and he was the master of the report and distributor of the report. But this really felt like one of the watershed moments for us, where we suddenly felt we had a lot to go. So what we wrote 27 years ago, I'm going to show you some text that looks very boring because it looks like what people write today. But precisely because it looked like what people write today, I still find it amazing that 27 years ago, we're sitting there writing all of this. We said history shows that significant advances in new discipline requires or gets facilitated by challenging driver applications. By that, we meant high volume. And one of those areas, we didn't know yet, this was 1994, before the introduction of GSM in Europe. Global wireless communications and local wireless wire-bound communications. Internet, in other words. We're bold enough to say that in 96, in 2 years' time, it will be 50 million subscribers. And before the end of the decade, it's going to be 500 million subscribers. So what we're preoccupied with ourselves is, what do we need to do to cope with that? And essentially we're saying design at a global level, at a system level, was so important. So this certainly changed the career or research directions for a lot of us. My group started doing tinkering with MOS technology for circuits a little bit prior to that, but this gave us the motivation. And indeed, no matter how brave we were in predicting that, we had no idea of the wild ride we were having. It's not exaggeration to call that, the last 30 years, the wireless revolution. And mobile phones are a product like no other. I believe they have tapped into something very deep in us and very profound. Our needs we didn't know we had until this thing was put in our hand. And then they led to the smartphone. It was fantastic to be able to talk wherever you go. But smartphone changed all of that. People say it's a smartphone. It's a handheld computer. And all this wireless is symbiotic with semiconductor. You look at those numbers, right? There are a couple of billion mobile phones every year, limited only by the population on the Earth. So volume stimulates integration, and integration enables volume. But it's more than putting more transistors on a chip. And RF CMOS was an example. Integration, what do you do? So this is a mobile phone on both sides of the board of the 1920s. How do you integrate that? This is the radio portion that measures 30 square centimeters on both sides. It has a lot of components: receiver, radio portion, intermediate frequency portion, analog baseband, transmitter analog baseband, transistor by IF, transmitter, RF, voltage-controlled oscillator, phase slot loop. All sorts of chips in there. And according to the Nokia executive during the meeting, he showed me this board, which I still remember today. Unfortunately, I didn't have a smartphone to take a picture of that. It had 600 passive components. So we really had a problem of production. Why do you want to have those passive off-chip components if you have transistors? Fundamentally, it's to manage dynamic range, to protect transistors from themselves from large interfering signals. What is dynamic range? Dynamic range is basically the smallest signal you can receive with the largest interfering signal present. It's like the ability to hear a whisper when other people are shouting nearby. How do you absorb or eliminate off-chip components? To do more integration, you basically need to improve dynamic range of on-chip transistor circuits. This, you need to have better architecture, system design, divide and conquer, try to do it. Now, where does CMOS come in? At the time, the incumbent technologies are bipolar, silicon germanium, gallium arsenide, and indeed, even as recently as 2018, people are still writing in trade magazine to say they're the top technologies. Bipolar transistor is a perfect transistor because its IV characteristic, the voltage and current characteristic, is exponential, really, really steep. And the derivative is good. And therefore, you have very good transconductance, very good speed, and sensitivity. But bipolar transistor does not follow Moore's law. It does not have exponential growth in terms of number of transistors. Not a cheap technology. Industry was not going for cheap, was going for quality. They would prefer bipolar. A lot of people still swear by the bipolar and gallium arsenide today. CMOS is fundamentally a cheap digital technology, very large-scale integration technology, VLSI. Cheaper because of Moore's law, cheaper because we can print a lot of them with this planar technology. And fundamentally, it is not exponential, it's some power function. But power functions are never as steep as exponentials. Therefore, lower GM and lower sensitivity. That was flatly dismissed by industry as unsuitable for RF circuits. I quote the same article back in the 20th century. That was so long ago. Right? It was almost unheard of even remotely consider CMOS for RF applications. They say the speed was not high enough. That's beside the point. Those 5 universities disagreed. And we pioneered this RF CMOS research step by step. I didn't quite crystallize this. Right? We thought, oh, well, it's a cheaper technology, we'll try to do it. But after a while, I start to rationalize. Right? CMOS is just as good in dynamic range. Granted, it will never be as steep as bipolar. But what it loses in sensitivity in GM Because it's not steep, it's not so nonlinear. Therefore, it's better in linearity. And in dynamic range, you need both. Therefore, if you want to do RF circuits in CMOS, you need to go for linearity. So that's where we kind of went. Lots of things were done. We had a fantastic grant, 1.7 million francs from Toshiba, and did circuits for the GSM technology and class, as already mentioned, did a lot of publications and so on. The latest of which, when we presented that at ICC, the director of RF systems of Infineon came to me and said, you have to come to Munich. And with them, we started working on 3G. I will skip the details here. Long story short, we published a lot of things with Infineon, and indeed, they took it into a commercial design called Smarty 3G, and that went into the iPhone 3G. So some of the iPhone technologies had their genesis here in Zurich. So architecture-wise, direct conversion architecture became an industrial standard because that is better for integration. In order to do that, this has been considered for a century before that. You need to overcome certain things. In receiver, you require the ability to get rid of what is known as flicker noise and offset, and the transmitter, you need to get rid of out-of-band emissions. But the payoff is if you can do that, then you get rid of what is known as intermediate frequency filters that are off-chip that are required for this. For the direct conversion, for the intermediate frequency architecture. But for 3G, it is based on FDD, the full division, frequency division duplex. It still has substantial external passive components. Surface acoustic wave filters are needed. This is a transceiver picture, and all the blue ones are off-chip, and you have that, all SAW filters, lots of them, costing money and space. The reason for that is because you're receiving and transmitting at the same time, and a fraction of the transmitted signal ends up in your receiver, saturating everything. So you need SAW filters to protect your receiver from that. If you don't want the SAW filters, because they're not integratable, then you need to improve the state of the art in the linearity of your modulator and the demodulator. Achieve that, then you can achieve SAW-less design. So we're very proud to have done that as well. And this has opened up opportunities, has made all those things into commercial. This is the first smartphone with a SAW-less transceiver for WCMA and all sorts of phones. Then, indeed, as Klaus mentioned, we carried on, had 4G transceivers. Now, more and more smartphones. You can see this particular portion, the external components are fewer and fewer, simpler, cleaner. And indeed, not only phones can do with those things, but also things that will benefit from it. On the right-hand side is actually something that's going to come to us soon in the next few years. It's called a vehicle-to-everything, part of the 4G plus 5G thing, where we will integrate a lot more wireless into cars. And 5G continues with ever more increasing complexity. If you look at the early phones with one receiver, one transmitter, now we have 20 of them. And this is kind of work in progress where all of those things are being measured. On 5G, so far, the wireless revolution was basically a single pursuit of higher bandwidth, higher throughput, higher data rate. So we didn't have a name. We just said broadband, data, broadband, extreme broadband, and so on. But then later we gave it a name because this has to do with human usage. It's called human type communication, HTC. But during 5G, people started thinking, and basically there are lots of machine-to-machine communication, and indeed, in the definition of 5G, there's a bifurcation where we separate human-type communication with machine-type communication, MTC. And machine-type communication is kind of interesting. So if you look at a 5G antenna, it supports various things. This is the extreme enhanced mobile broadband, which is our latest smartphone with the highest data rate. And there's a thing called massive machine-type communication. And also, there's a third part, which is called the ultra-reliable, low-latency communications for Industry 4.0. So people were wondering, the HTC is saturated because there are only 7 billion people in the world, so that you have about 1.5 billion phones sold every year. But there are new things coming up, and people are talking about next 10 billion devices, next 100 billion devices, because they're not limited by humans. I won't go into details, but essentially they require high integration level because now they are dealing with things, they need to be small, and also much better sensitivity because they're going to be in the basement, buried in the pipes, all sorts of different places for application. This is work in progress, our latest publication, where we introduce this, or we are competing with other groups in working on cellular IoT system on a chip. And I will just spend a little bit of time in the context of design. Because it's a necessity to integrate everything for Internet of Things devices, we have everything on a chip because it needs to be done, and we have global optimization for it to have high performance. We have RF transceiver, we have digital baseband accelerators to do things fast without consuming too much power, RISC-V processor, which our institute is famous thanks to Luca and her co-workers, tightly coupled data memory, not only for the processor, but also for our accelerators, sophisticated power control for consumption, and so on. Just one slide here. This is a template of how LTE, our 4G, 5G signals are organized in time and frequency with synchronization reference symbols in between. But the key thing is, if you look at those signals in detail, the signals are buried deeply below noise. The signal-to-noise ratio is negative because you're in the basement, because you are 10 times further away than your normal. It's called extensive coverage. In order to receive such signals reliably, you need to do a lot of signal processing, algorithmic level of optimization in order to do that. And if you're able to do that, this is almost like digital signal processing level, but it really looks like analog design because you're playing with the compromises and trade-offs. So we managed to get state-of-the-art in all of that. To give a sense of what that means, this was the same phone, two sides of that radio board of the 90s. And that little module is today's triple mode SoC module. 2 power amplifiers plus a device like that. So we've come a long way. And this is not your grandfather's radio modem anymore. So to design a complex system like that is really like a multitude of moving targets that need to be shot, and in one bow action. You need enough fingers to hold all of the arrows, kick up the tomatoes, and shoot them in place. If you can do that, if they're all on target, then you can stay on that rising exponential. So all of those things were on the internet side of the IoT. How about the things side of the IoT? So you need those devices that interface with sensors and so on. And they're called sensor nodes. They're typically small, space-constrained, in wearables in size, weight, and power, implantables in size, weight, and they need to be powered in the first place. So to see the challenge of such miniaturization, you need all those components, sensors, analog front ends, amplifiers, converters, passive filters, controllers, RFIC, crystals, power supply, LDO DC converters, battery charger, decoupling cabs, interconnection. And before you know, it's a fairly complex device. And when we started doing this, some of the people said they had Gruppenarbeit with me. It was huge, it was a big board. So even as we did this to a handheld, we were very proud, but ultimately, it needs to be much more integrated, and we've come a long way. Generally, for IoT stuff, you don't have enough, the applications are fairly fragmented. For example, even for health, right? You have ECG, EEG, PPG, optogenetics, and so on. And most of that will require miniaturization and software, and classes students would not want to spend all their years hooking the electronics together. They would like to use it, and it's not their job. And therefore, we're thinking we should make a one platform for everybody to use, and we'll have capture all the commonalities. So we have this SoC called VivaSoc, okay? And we built a module based on it, which is very small. And also with the module, you can actually build cheap PCBs very quickly, and so on. And indeed, lots of software needs to be written, and we can have one app for all, monitoring, device control, data readout, firmware update, all of that. Then it's nice. So we have a run of mobile health applications, basically supporting different needs, and this is one of the examples where your application, your health indicators are literally at your fingertip. But what I would like to highlight is one of those things where you have miniaturized instrumentation that help scientists do what they couldn't do. This is optogenetics, which is essentially you modify the genes of some of your body parts so that it will be sensitive to light, and you can do control and other things. The head stage that we are responsible for is tiny. It's about a little bit more than a gram in weight and just less than a cubic centimeter, including the battery. But it really opens up very interesting applications where we have these co-workers in Lausanne who did fantastic, amazing things with our stuff. So here is the whole thing in action. You can do closed-loop control. You can actually have wireless viewing, previewing to first see where you should set your threshold and so on, and have on-chip calculation and determine exactly what you need to do. And then you have closed-loop control where you can actually control, for example, the gait of the mice, the rat. If your simulation is off, it has a particular step size, and if you have simulation on, it has a different one. So it's just an example where engineering enables advanced science to be done. So all of this is fantastic. It really makes you very, very optimistic. The world is ours. We have great expectations. We could do AI, data analytics, big data, 5G, V2X, smart home, Industry 4.0, wearables, personalized medicine. And indeed, European Commission is very excited. We do this digitalization again, digital transformation for others. all of the things. The all is not well. So I can think of no other way to express it than the couple of books I've read before, the state we're in, and the world we're in. The steep rise and fall of fortunes create dissonance, and both nationally and internationally. And there are haves and have-nots. And the people who have and the people who have nots may not share the same vision for the future, either politically or economically, or about our own body. So the balance between competing exponentials will never be easy, and the temptation to tilt it to one's favor is always very strong. What do you do when the chips are down? And I don't mean it figuratively. They literally are down. So suddenly, when they're there, you didn't notice there were chips. You only notice when they're not available anymore. And the semiconductor have and have-nots have really shaped a lot of the debate. So the last competitors, Samsung and TSMC, are spending 30 to 50 billion of their own money per year to stay on that race. And indeed, TSMC has a commanding control of the 60% of the world's semiconductor production. And if you look at this, once upon a time, Europe and the United States have 80% of the integrated circuit manufacturing. Today, together, we account for 20%. The rest are in Asia. People wouldn't be nervous if it weren't so fundamentally critical to us. If you pay attention to semiconductor news, like I do, every nation basically says we must have our semiconductor self-sufficiency. It's like having your own airlines. Now, almost there. Having semiconductor manufacturing is important, but it may not be everything because that Moore's law is coming close to an end. It's question one, and Gordon Moore himself, on the 50th anniversary of the Moore's law, said no exponential is forever, but forever can be postponed. So we've had another 10 years, but eventually it's going to be slowed down by economics, by diminishing return of what you do. So when everybody has the same transistor, then the design may matter a lot more. And for new products, for mobile phones, it's saturated to 1.5 billion, and the surviving players very much carve up that thing. But there are new things like IoT and so on. There are new exponentials that are on the rising part of the curve before the hockey stick. And that is where it matters. The integrated circuit design is a race we cannot afford to lose. Without the control of the chip, you say, oh, we just work on software. You can't even prevail in software because the competitor controls the platform on which you can write your software. So the rescue for that may yet lie in the design. For university, we can't spend $30 billion or francs, but we need to do for the society what we can do. So the least thing we can do is to educate students. And indeed, design is considered an urgent matter of national strategic interest for the United States and for Europe as well. We cannot just sit and say, okay, let China and US divide. We have been a bastion in integrated circuit design and the education of integrated circuits. And I believe the Institute Integrated System Laboratory is in good hands. When I came here, I was the only IC designer. Now we have 4, and they're highly recommended. So here's my parting shot. Integrated circuit has 15 billion transistors and counting, and the future is integration. Volume reduces cost, integration increases volume, all or nothing. It is the way of the exponentials. The future is system design. You need to manage complexity and the trade-offs, shoot multiple arrows in one shot. Global optimization makes all the difference. You need to make every transistor count, and you better do it right the first time. Remember that capacitor that tilts the flip-flop, the latch to the other direction? Being late is not good. The future is also system on a chip. You cannot leave any functionality behind. You need to manage, even if you manage supply chain logistics, have a single chip is better than having a collection of chips. Integrate digital, analog, and RF. And we joke that there is an axiom without need for proof. If a function can be integrated in CMOS, it will. When the chips are down, cast it all on a single die. On that note, I'd like to thank Qiuting for giving me the opportunity to work on those things, the department for providing a fantastic working environment, for providing the funding, for all my generations of students who actually did many of the innovations and made us put the ETH on the map. And last but not least, my family, who put up with my traveling and absence and long hours on the computer. Thank you.